Hello students, myself Sachin Ugale, and today we are going to discuss about the third part of the chapter Electrochemistry. In that we are going to discuss dependence of cell potential on the concentration, that is also known as Nernst equation. See in the slide, dependence of cell potential on the concentration in bracket, that is known as Nernst equation. We know that in the previous lecture we discussed that the cell potential is depend on the concentration, pressure as well as temperature. So this topic is concerned with the dependence of cell potential on the concentration. Now the standard cell potential tells us whether or not the reactants in their standard states form the product in their standard states spontaneously. That means whether the spontaneous chemical reaction is feasible or not, we can predict from this equation. So let's see how it works. For any general reaction, consider a general reaction. A moles of A, that is a small a, indicates the number of moles, and there is a capital moles indicates that concerned element. So A moles of A plus B moles of B, that means that is shown by arrow, that gives C moles of C plus D moles of D. The cell voltage is given by, now for this, how to find out the cell voltage? So we can apply the following equation to find out the cell voltage. E of cell is equal to E0 of cell. Now this E0 means standard cell potential. So E0 of cell minus RT divided by NF ln in square bracket C, capital C is written, and raised to, or the power of that again C, that means that are the number of moles. So when we write any element in square bracket in the chemistry, that is read as its concentration. Okay, when we want to see a concentration in mathematical form, so we write that element in square bracket, that may be ion or any molecule or something. So when we write in it is in a square bracket, that means it is indicates a concentration of that concerned term. So ln concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. So same thing we can write as, if we want to remove that ln, so we can write E0 of cell minus 2.303 RT. So when we want to remove that ln, we know that we multiplied that term by 2.303. So 2.303 RT divided by NF, as it is log to the base 10. That means instead of that ln, we are written now log to the base 10 into concentration of C raised to C, concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Where now what it indicates, where N is equal to, that means N means number of moles of electrons. So N indicates number of moles of electrons used in the reaction. That means that concerned reaction, how many moles is used, that is denoted by a small n. Then F is a Faraday and its value is 96,500 coulomb. Then capital T is a temperature in Kelvin and R is a gas constant and its value is 8.314 joules per Kelvin per mole. At 25 degrees Celsius, if we are conducting this reaction at 25 degrees Celsius, then 2.303 RT divided by F, if we substitute all these values at 25 degrees Celsius, then we get the overall answer of this term, that is 0.0592 volt. That means instead of writing all these terms every time, we can write 0.0592 volt. Therefore at 25 degrees Celsius, the equation becomes E of cell is equal to E0 of cell minus 0.0592 volt divided by that N. N means number of moles, moles of electrons used in the reaction. Log to the base 10 into C moles of C, concentration of C moles to C divided into concentration of D moles to D divided by concentration of A moles to A into concentration of B moles to B. If we consider the concentration of all these elements, that is concentration of A is equal to concentration of B is equal to concentration of C is equal to concentration of D is equal to 1 molar. That means every term having a concentration of 1 molar. In that case or in that condition, E0 of cell becomes E of cell. Okay, so this is a very nice equation. E cell is equal to E0 of the cell, but only when if the concentration of all the terms is equal to 1. So if or sum of the reactants or the products are in the gaseous phase or the gaseous state, then what to do? If the gaseous substances is present in the cell reaction, its concentration term is replaced by the partial pressure of the gas. The Nernst equation can be used to calculate the cell potential and electrode potential also. So we can apply this equation to calculate the cell potential as well as individually electrode potential also. So we just try to apply that for the concerned cell. So the first case, calculations of the cell potential. That means there are given one cell is there, that is consider the cell CD, that is cadmium, that is in solid state, that's why its physical state is written in the bracket. Then single vertical line, that means this CD is a electrode and that electrode is dipped in CD2 plus, that is the ionic solution, or that is again an aqueous solution of that CD. So that's why they are written. We know that how to write the how to represent the cell. Then double vertical line, as I told you in the last lecture, double vertical line indicates salt bridge. That means they used a salt bridge in this cell. Then Cu2 plus, that means copper's ionic solution, and that is again aqueous one. Then single vertical line and Cu, that means they used two electrodes, that is CD, and the other one is copper. Again, CD electrode is dipped in its own ionic solution and copper electrode is dipped in its own ionic solution. Again, they are connected with the salt bridge, that's why they are shown a double vertical line in between them. So this is the one of the cell. So we have to calculate the cell potential of this concerned cell. So for that we have to write the cell reactions. So let us first write the cell reaction CD, as I give some hint how to write the cell reaction in the previous lecture, that is LOAN. The one hint is given to you in the previous lecture. L stands for left, O stands for oxidation, A stands for anode, and N stands for negative. So according to that hint, we can write CD means that is the left side electrode is there, that is oxidation, that means loss of electron. So CD gives CD2 plus 2 electrons, that is a oxidation at anode. Below that copper, so that is a right hand side electrode, so that is a reduction. So Cu2 plus 2 electrons. So electrons is written at the left hand side of the arrow, that's why there is a acceptance of electron. So Cu2 plus 2 electrons, and that forms a neutral Cu, that is a reduction at cathode. So the net cell reaction, when we write the net cell reaction, so we write all the elements or all the species at the left hand side of the arrow to the left hand side in the net cell reaction. So CD plus Cu2 plus, so there should be 2 electrons, again 2 electrons, that gives CD2 plus Cu plus 2 electrons, but that 2 electrons get cancelled, so that is a direct return of the overall cell reaction, that is a Cu plus Cu2 plus, which gives CD2 plus Cu. So in the next slide we can see here N, that is the number of electrons participate in this reaction, is 2. So the potential of the cell is given by the Nernst equation. We know that E of cell is equal to E0 of cell minus 0.0592 divided by 2. That is n's value is 2. That's why here it is written 2. Log to the base 10 and the concentration of CD2 plus divided by concentration of Cu2 plus at 25 degrees Celsius. They are given at 25 degrees Celsius. That's why we are direct substituted that value of 0.0592 because this reaction is carried out at 25 degrees Celsius. Concentration of solids and pure liquids are taken by unity. They are given in the bracket. When the concentration of pure solid is there and a pure liquid is there, then its concentration is considered as unity. So by using this formula, we can calculate the cell potential of that concerned cell. Now the second case, in the second case we will try to calculate the electrode potential. So consider a half cell, that is Zn2 plus aqueous is in the vicinity of Zn. That means zinc electrode is used, or the zinc electrode is dipped in its own ionic solution. The reaction for the electrode is Zn2 plus 2 electrons that forms a neutral Zn. Applying the Nernst equation to this to calculate the electrode potential, we can E of Zn is equal to E0 of Zn minus 0.0592 divided by 2. Why there is 2? Because 2 electrons are there in this reaction. So that's why there is a 2. Log to the base 10 into 1 divided by concentration of Zn2 plus ions. Zn2 plus ions. So it becomes, if we use some mathematics in that, so we can write E0 of Zn plus, now in the previous equation that was minus, in this equation that is plus 0.0592 divided by 2, log to the base 10. Now concentration of Zn2 plus at 25 degree Celsius. There is some mathematical changes is there, but the overall value of that equation remains as it is. We know that. So by you applying this formula, we can calculate the electrode potential of a concerned electrode. So we just now saw how to apply the Nernst equation to calculate the cell potential as well as to calculate a electrode potential. It is a very simple one, and by the value of a Nernst equation or the cell potential or the electrode potential, we can say that whether this reaction is spontaneous or non-spontaneous. So now the next one, thermodynamics of galvanic cells. In that gives the energy of cell reaction and cell potential. The electrical work in the galvanic cell is the electricity or the charge passed by multiplied by the cell potential. What this says, electrical work is equal to amount of charge passed into cell potential. So this is the formula for electrical work. I'll repeat once again. Electrical work is equal to amount of charge passed into cell potential. So the charge of 1 mole of electron is F coulomb. We know that the charge of 1 mole of electron is 1 Faraday is there, 1 Faraday. For the cell reaction involving n moles of electrons, we can write the same formula as charge pass is equal to nF coulomb. Hence, electrical work is equal to nF into E of cell. So, electrical work is equal to minus delta G. Now, this equation is given by W. Gibbs in 1978. Concerned that electrical work done in galvanic cell is equal to the decrease in Gibbs energy. That is, that there is a decrease, that's why it is a delta G, minus delta G of the cell. It then follows that electrical work is equal to minus delta G, and thus minus delta G is equal to NF into E of cell, or the same equation we can write delta G is equal to minus NF E of cell. That means in any equation we know that if the one of the side right hand side or the left hand side is equal to the each other, then the whole equation becomes as shown. Now in the next, standard cell potential and the equilibrium constant, they are given in the slide. Remember, for the chemical reaction to be spontaneous, delta G must be negative. This is a very important point. It is most probably asked in the MCQs, whether the following reaction is feasible or not. For that, if the reaction is spontaneous, then what they say is, for the spontaneity of the reaction, delta G must be negative. So we can observe the reaction or the value of delta G, we can say that whether it is a spontaneous or the non-spontaneous reaction. So remember that. Then next to that, standard cell potential and the equilibrium constant. So for that, as they given, minus delta G0. So always remember, when we write at the G0, that means its standard value is considered. So standard cell potential and equilibrium constant. So minus delta G0 is equal to NFE0 of cell. That means Gibbs free energy is considered as standard state, as well as E of cell is also considered at standard cell. So in the next equation we can write delta G0 is equal to minus RT ln K. Minus RT ln K. So these are the two equations. By combining these two equations, that means left hand side of the both the equations are same, so that right hand side also becomes same. This is the mathematical rules are there some. So minus NFE0 of cell is equal to minus RT ln K, or the same equation we can write E0 of cell is equal to RT and F ln K, but that means this is just a rearrangement of this equation. We get, or we can substitute 2.303 instead of that ln. So we can multiply that equation by 2.303. We know that this is the mathematical rules. So 2.303 RT divided by NF log to the base 10 into K. These equations are considered standard state, so we can substitute the value of that 2.303 RT by 0.0592 divided by N into log to the base 10 K at 25 degrees Celsius. So this is the relation between standard cell potential and the equilibrium constant. So we can apply this equation for to solve some problems, or to understand this equation we have to read some theory again related to that. Now the next point is reference electrode, that is a standard hydrogen electrode, in short that is called as SHE, in the next lecture. Thank you.